Welcome class, thank you for joining me for 8.7 and congratulations, this is our last notes of chapter 8. You've made it all the way through. Today we're going to be talking about factoring the difference of squares. Now what that means is we're going to be looking at the form a squared minus b squared. And I will get back to that in just a second. But before we begin, I want to just review what we did in the previous notes. So first we're going to factor this, 21y squared plus 72y minus 48. Back to one of our basic quadratic trinomials. So the first thing that I'm going to do is look to see, can anything pull out? Well, I don't see my variable in every term, so I'm not going to pull a y out. But something that I notice is a 3 can be pulled out of everything else. So I'm going to pull a 3 out of every term, which is going to leave me with 7y squared plus 24y, oh, I'm sorry, 24y minus 16. And now that that's what we have left, remember, we take that inner portion that's still inside the parenthesis, and now I break it down just like we did in all of the other notes. So that 7 represents 7 times 1, and 16 can be 1 and 16, 2 and 8, 4 and 4. And because there's only this 7 and 1, I know that the basic structure of this is going to be 7y and just y. Another thing that I notice is that those negatives, all right, our C value is going to be negative. So as I'm plopping in numbers, remember that means one of those little arcs, one of those little connections is going to end up being negative, and that's where the 24 is going to come from. So I'm going to first plop in the 1 and the 16. Making my connection, so that gives me 1, and 7 times 16, 112. So making one of those negative, we're either going to get 111 or negative 111, not the 24 that we're looking for. So I'm going to erase that, and I'm going to switch it. 16, oh, not 7, 16 and 1. So make those connections. That gives me 16. That gives me 7. All right, well, again, knowing one of them is negative, that's going to give me plus or minus 9. Still not what we're going for. So what that means is the 16 and 1 is ruled out. So let's try the 2 and the 8. Make my connections. We get 2, 56. So again, knowing that one of those is going to be negative, we're getting plus or minus 54. Still not quite what we're looking for, but let's reverse it. 8 and 2, that's going to give me 14 and 8. But again, knowing that one of those is negative, that's going to give us 6 or negative 6. Still not what we're going for. So we can rule out that one. And our last option, so I hope this works, we connect that to get 28, connect that to get 4. Knowing one of those is negative, we get plus or minus 24. Now, to get the positive 24 that we're going for, we're going to need a positive 28 and a negative 4. So we need a negative there, positive there, and that is going to give us precisely what we are looking for. So don't forget, that's the process we do when we have a quadratic trinomial. Now, there are some special problems that can't be solved that way. So I'm going to review really quickly. When we FOILed something that looks like this, remember, we ended up getting that. So, since we're talking about unfoiling, we need to talk about what to do with that case. what happens when we start with the form a squared minus b squared? Now this is called a difference of squares. And when you can identify them, these actually end up becoming some of the easiest things to factor. There's a couple of things you need to know about it though. First, to be a difference of squares, it needs to be a binomial. And again, a binomial meaning two terms. So we're no longer looking at three-termed things, we're looking at things with merely two terms. And must be subtraction. So far, we're talking about two terms, subtracting on the inside. The last thing is both terms must be perfect squares. So let's recall perfect squares. So there's a couple criteria to determining what a perfect square is. So I'm going to jump down here to perfect squares. So in terms of numbers, what numbers make perfect squares? Well, that would be this list. 1 is a perfect square. 4 is a perfect square. 9, 25. Oh, I forgot 16. 16, 25, 36, 49, 64, 81, 100, 121. All right? And the list keeps going. But the idea is that list of perfect squares, the way you can identify them is if it has a nice square root. If you can take the square root of the number and it gives you a whole number, that makes it a perfect square. Now, for variables, focus on here for a moment. For variables, any even power on a variable makes that variable a perfect square. So, for example, you look at this 4x squared. 4 is on our list, and the variable has an even power, so that makes it a perfect square. That gives it the ability to break down into 2x times 2x. And then minus 9, 9 is also on our list, which is 3 times 3. And what ends up happening when we do that? Well, when you can break it down that way, the basic structure is you get two parentheses. You know the first one is a plus, second one is a minus. So it's 2x plus that 3, 2x minus that 3. That's all you have to fill in, and you are completely done with the problem. That is all a difference of square is, having the plus and that minus relationship in the two parentheses. So just to get a feel for this, we're going to do quite a few examples to help you understand what's going on here. So on the side here, these, again, are the numbers that we are looking for. Right? And again, the list does keep going on and on. So let's look at this first example. So 49x squared. Well, let's see, what can I break that down into? Well, 49 breaks down into 7 and 7. X squared is x and x. So it is a perfect square because 49 is on that list we can take the square root of, and we have an even power. And 100, one of the easier of the squares, breaks down into 10 and 10. Second thing to check for, make sure this is a subtraction problem, which it is. So both of those terms are perfect squares. It is a subtraction problem. So we can take the basic form of the difference of squares. We get 7x plus that 10 and 7x minus that 10. And again, that's already the end of our problem. That is all that we have to do. So let's keep looking. So for each of these again, I'm going to break it down. So that x can be broken down into x and x because it has an even power. That 9 is 3 and 3. So both things are perfect squares for me. Next thing I notice, it is a subtraction problem. So it meets the criteria of being a difference of squares. So I set up my structure. Knowing one is plus, one is minus, we're going to get x plus 3, x minus 3. Looking at number 2. Again, 4 is on that list of nice numbers. It breaks down into 2 and 2. X has an even power, so it is just x and x. And the 25 breaks down into 5 and 5. So again, we are talking about two perfect squares here. Checking, it is a subtraction problem. So we are going to put it in our basic format. 2x plus 5, 2x minus 5. Now, number 3. Number 3 has a little bit of an issue. The first thing that I notice, it has a plus there instead of a minus. So before I do anything, I can already rule this out of being able to be a difference of squares problem because it's not subtraction, it's addition. So I'm going to cross that one off right away. That is not what we are looking for. Now going to number 4. If you notice, here we have a higher power. Here we have a y to the 4. But remember, anything with an even power is a perfect square. Well, 36 we know is 6 times 6. Now y to the 4. Now the cool thing about y to the 4, since we're looking for perfect squares, we know we're going to be looking for y squared and y squared because 2 plus 2 gives us that 4. And 1 is one of the most basic perfect squares, 1 times 1. The square root of it is itself. We do have subtraction here. So that means I can set up my structure. This does meet the requirements. So set up my two parentheses, plus or minus 6y squared plus 1, 6y squared minus 1. Number 5. 16 is on our list of perfect squares. It is 4 times 4. X to the 4, well, we just talked about that with that y to the 4 in the previous one. So when you break it down, we just get x squared and x squared. 2 plus 2 gives us that x to the 4. Check to make sure we're talking about subtraction. And now make sure you're putting this in the right order still, all right? Because of the order it is in the original problem, we're going to have 4 plus x squared, 4 minus x squared. Make sure you're going in the order of the original problem, okay? In this case, our variable is in the second piece, so that's what gets plused and minused. Number 6. So x squared is a perfect square, x times x. Now, when we get over here to the 10, 10 is actually not a perfect square. If you try to take the square root of it, you're not getting an integer. You're not getting a nice number. So in this case, number 6 is another example of something that is not a perfect square or is not a difference of squares because 10 is not a perfect square. That one we can cross off. We can't end up solving it using this method. Continuing on though, number 7. That variable has an even power. So we know we're talking about x times x. 1 breaks down into 1 times 1. We are dealing with subtraction. So I can set up my structure, that plus or minus. So x plus 1, x minus 1, and we're done with the problem already. Number 8. This one is a little bit different. So notice the 20 and the 45. You may look at this at first and say, well, those aren't perfect squares. I can't do anything. However, the first thing I want you to note is the fact you can actually factor out a GCF. I want you to realize that both of those numbers are actually divisible by 5. So the first thing that I'm going to do is pull out the GCF in this case. I'm going to pull that 5 right out of the rest of the problem. So I'm going to get 4x squared minus 9 left after I pull that 5 out. And now if you notice that inside portion, both of these are perfect squares now. The 4 breaks down into 2 and 2. The x squared breaks down into x and x. 9 is on our perfect squares list. It's 3 and 3. It is a subtraction problem. So now we can actually still set up that perfect square or that difference of squares scenario. 2x plus 3, 2x minus 3. And being careful to remember, you have to pull that original 5 down. Okay, when you pull it out, you need to keep writing it there. So note, some of these may be deceptive. They may not look like a difference of squares to begin with. However, when you pull out a GCF, sometimes they will transform into one. Perfect example of that. Number 9 does the same thing. Notice, you have 6's in there. 6 is not a perfect square. However, if you pull it out of both of those terms, now what you have left is able to become a difference of squares problem. That x to the 4 breaks down into x squared and x squared. The 1 breaks down into 1 times 1. Double check, we are talking about subtraction. So I set up my parentheses for my difference of squares. X squared plus 1, x squared minus 1. Make sure you pull down that 6 that you had originally pulled out. And there's the end of our problem. Our last one, number 10. So this one's kind of a challenge problem for you guys because these are getting to be really big numbers. Now, 625. Since you see the construct happening here, the variables have even powers, it's a binomial. So even if you're not sure if those are perfect squares or not, the 625 and the 121, I'm hoping that you will at least know to check to see. Pull out your calculator. See if the numbers work out. Because when you check these, what you will discover, 625 is a perfect square. It is 25 times 25. And again, x squared would break down into x and x. 121 is 11 times 11. And then w squared breaks down into w times w. So both of those things end up being perfect squares, and we are subtracting. So this actually does become one of our situations, our difference of squares. So I put my plus or minus there. So 25x plus 11w, 25x minus 11w. So thank you so much for joining me for this final notes. Please make sure you have all this written down. We will wrap up in class, and then we will soon be done with Chapter 8. So again, thank you for joining me, and make sure you have all of these written down.